This is section 1412 called Analyzing the Fragments in a Mass Spectrum. Whenever a molecule undergoes mass spectrometry or is injected into a mass spectrometer, the instrument, bombarding molecules with electrons tends to cause fragmentation in the molecule. So your book has a nice example of pentane, whereas whenever you bombard pentane with electrons to make the parent ion, it undergoes fragmentation in 4 key ways. Either you can lose a methyl group, lose a methyl group here on top, lose an ethyl group next, lose a propyl group, or lose a butyl group to leave you just with a methyl. You'll notice that the top one and the bottom one go together, because when these fragment, you'll see not only the top, but also the bottom one. And whenever you fragment to get a propyl and an ethyl group, you will also see both of those. And the mass spectrum of this type of process looks like this. And this might look familiar to you from the sections previous on identifying the M+1 and M+2 peaks, because each of these is separated by 14 mass units. So you have the parent ion, and then 15, which is that loss of a methyl group there. Then you have -29, which represents the loss of the end methyl and the next methyl. 43, which is the loss of all but 2 now of the carbons. And then 57, which is just the lonely methyl ion. No matter how large, alkanes typically break up in this manner, where you can imagine making fragments in the same way, even with much larger molecules, such as icosane that has 20 carbons. You can still see the molecular ion peak, and then roughly every 14 mass units, you see another set of peaks that corresponds to different molecular fragments. So whenever you're looking at the fragments, understanding their proximity to the molecular ion peak is very important, because that can tell you what exactly you're looking at in terms of the functional groups. So the other thing is, we've only talked about linear alkane groups, but you can also do mass spectrometry on alkanes that are not linear. And if you do this, the most likely fragmentation that you can see is if you do mass spectrometry on this molecule, the largest fragment you'll see is this one, the tertiary carbocation. And that's because the tertiary carbocation is the most stable. And typically, the base peak that you see in mass spectrometry is the one that is the most stable. So that's something to keep in mind. The carbocations there follow the exact same stability rules as did the carbocations in our reactions. Now, other functional groups can undergo different fragmentation as well. So an alcohol can undergo fragmentation, but typically they undergo alpha cleavage and dehydration reactions. So in an alpha cleavage, the alpha carbon is cleaved from the rest of the molecule through this very weird single electron transfer reaction. And this only happens because you've knocked off an electron with an electron beam. So you make this molecule or this one, both are charged, so it doesn't matter, plus the alkyl radical that you don't see in the mass spectrometer because it has no charge. You only see charged species in the mass spectrometer. So with the resonance stabilized carbocation or oxonium positive ion there, probably it's going to be the carbocation, you can detect this molecule, which is typically the parent ion minus this group. Also, the alcohol can undergo dehydration, just like we saw from our alkenes chapter. And this will be loss of a water molecule. So since it's loss of a water, it will typically be the parent ion minus 18 because water weighs 18 mass units. Of these two, the easiest one to spot is definitely the dehydrogenation product, or sorry, the dehydration product. So you should always look for an M-18 peak to see if there's an alcohol present in the spectrum. Because if there is an alcohol present, it's more than likely that you will have an M-18. Amines undergo some similar things, except they don't have the dehydrogenate or the dehydration reaction to do. So often you will have some much more complicated fragmentation. And ketones and aldehyde also undergo fragmentation, but in a very weird way, because if you have a gamma position available, you will do this type of single electron transfer rearrangement, where it's called a McLafferty rearrangement, and essentially you end up with a different positively charged oxygen species and an alkene. You don't see the alkene. However, this alkene, it weighs, let's see, that's 15, 30, 45, 60, 72, 84. You wouldn't see this one, but this ion would weigh M minus 84. So it would be useful to remember each of these functional groups and how they fragment. Here in table 14.3 is a nice example of common fragments that we see in mass spectrometry. This is probably the best thing to look at if you want to learn more about how to interpret the mass spectra up to now. And also, this is the type of stuff I will expect you to know on a test. One thing that I will do before we stop this session is go through with you some actual real world data. Yeah, that's what I want, Google Chrome. Okay, great. Some real world data for molecules like octane. This is an alkane. Octane is C8H18, and you see that we have the molecular ion peak, and then fragmentation starts. So 114 fragments to 85, which is 29. And then every 14 after that, we see fragments, with the base peak being here at 43. We know from our little table that we just talked about, M-43 is loss of a propyl radical. So we can look very easily at what type of fragmentation is occurring and how to identify the molecules. Another functional group we can talk about are the amines, but they're much more difficult to understand their fragmentation. Here is one pattern where you have the molecular ion at 73 for butylamine, which is C4H11N. However, the base peak is at 30, and it's harder to say anything else about that. However, for butanol, it's a lot easier. The molecular ion peak is at 74, and then minus 18 for water is 56, and there's our base peak. So we see that, again, a loss of 18 is water, and our table tells us that 18 is loss of water from an alcohol. So please make sure you know the information in 14.3 and keep your mind open to lots of fragmentation possibilities. And this was section 14.12.